Yes.
My name.
Yeah, you can start. Okay.
Oh, I think I put the wrong letter. I should get this one. So this is this.
University of Darmstadt. Then I would like to present our work on types of.
It is okay. Thank you. So this is the part I would like to present to you. So I will start with WAF now to show how we can now try to capture the primary and secondary backup. And I will start with oh, what it is. Excuse me again. This okay. I will start with the WAF part, and then first using LES, including in nozzle flow and first change, and then I will show you how we have tried to record comprehensive data using DNS, WAF, and then we have developed a technique to treat the droplet statistic in order to get a correct idea when we use, for example, LES. And this was validated by DNS. And then I will show you a work on WAF Lagrange coupling in a real-time way. So the impact of atomization process on the morphology of gasoline direct emission jet is of great importance if we account for the fact that in stationary fuel injection determine the structure of injecting jet, and this strongly influences the initial droplets distribution, and this determine also the evolution of subsequent downstream processes like evaporation, the mixture formation, ignition and combustion. That is what we will do later on, but not in the frame of this presentation. Here we focus only on WAF. And we can also have an interaction between the jet and the surrounding in-cylinder flow conditions, so that there is the so-called cycle-to-cycle variation, for example, in IC engine. And to capture that, it is necessary to include also the in-nozzle flow in order to capture the whole development of the flow. So the objective is to investigate the effect of this stationary flow injection. And first we use LES, and we try to extract the initial droplet size distribution for the Lagrangian method. So we have developed this WAF LES approach, and okay. So we would like to extract also the initial droplet size distribution for a Lagrangian method. So this is the central point, how we can extract initial droplet size distribution for a Lagrangian method. So to get them from WAF and to put to Lagrangian, The first idea was to prescribe an interface and to generate the droplet distribution at this point to and then to put them to Lagrangian. And the next point, the next issue was to see how this generation can be reliable. And for that, we have developed a comprehensive, we have generated comprehensive DNS data. And from this DNS data, we have tried to validate this methodology we have developed here. So then that is why we started with this WAF-LS approach, and in which we introduce phase change. I will show the computational setup. We will start with the spray G. It is the SCN spray, the spray G2, and then for the DNS, we will use the spray G3, and then we will try to see how we evaluated these different data. So the LAS equations are what we know, say the continuity equation here, because we assume that we have only one phase formulation. And then we had the Navier-Stokes equation, and here the question for the energy. I hope that all these quantities are well known as we have introduced them previously yesterday. And for the WAF with phase change, so we have this part for WAF, the liquid volume fraction, and we have here different terms. The first term, it is the compression term, and here we have the term which account for the phase change, and here we have the additional term which account for the compressibility, possible phase change. Now I can say for the density variation. And this is the volume fraction of vapor. It is normalized, and it is normalized in this way. We add this compression term to make everything stable. And here it is equivalent to this one, and this one is also equivalent to this. So having this, we try, we select, excuse me, we have selected this configuration, SCN spray 2. It is a configuration which is characterized by 8 nozzle holes. We have the needle, and for this G2, we have needle movement. I will present you all the operating conditions. The injector, and we have iso-octane as a fuel. And we use, normally we have, I think, chose only one part here, 45 degrees, which represent our computation domain. And this was the nozzle, the needle movement. And we have the ambient gas temperature, the saturation temperature, and the saturated temperature, the pressure temperature, so that we can say we have the phase change in this in this in this configuration. So that is subject for the computation domain. For the inflow, for the boundary conditions, so we use the cyclic boundary condition here. We have the wall there, and we have moving wall. The inflow is here, and the numerical setup consists in a block structure at the grid with a cell with a value from 1 point with a grid size of this year, 5 to 20 micrometer. And here the grid is 1.2 million cells. and the inflow condition dependent, time-dependent mass flow as provided by the ECN. And we have the needle movement adapted piecewise in 4 intervals. We have the moving mesh to account for this here. And we have also layer additional removal technology as provided by ECN to get correct flow in our ECN spray. The cyclic boundary condition, as I told you, has been used, and we solve everything with open form. The first result, we have the opening time and the closing time. So we have 2 times here, the first one T1, and we have also result for T2. So here we have the liquid volume fraction for, we see its evolution at this time and the velocity also, and for the vapor, it is only to see the evolution within the nozzle and outside the nozzle to this time T2. And we can see that we have formation, still already formation of droplets at this area, and with high velocity at the outside, at the outlet of the nozzle. And for the vapor, we have also vapor formation here, so that we can say we have our 2-phase flow. We try to compare the plane cone angle with the experiment, so we got that our beta is 14 degrees, and from the experiment, it is almost the same. So the task was, if we have this, is it possible to generate droplets size distribution at different position? And if we have this distribution, how we can be sure that it is correct if we don't have experimental data? Because if we want to carry out Euler Lagrangian, so we have to provide flow distribution and droplet size distribution to the Eulerian part. And if we have no experimental data, so sometimes it is difficult to prescribe this droplet size distribution. It cannot be directly known. For the simple case, people use Rosen-Lambda distribution, but here we have developed these techniques here. What is the first step? The first step is to select a threshold, and here we took the liquid mass fraction of 0.5 to characterize the liquid region for each slice. Here we have 5, and with this selected value, we obtain a distribution of liquid at this plane. Then we try to separate connected liquid fragments, and for that we use erosion process with an operator of this size here. It is 2 times larger than the grid size. With this erosion, so we separate connected liquid fragment. And after that, we did a dilatation to recover the same mass as before. And then after dilatation, so we obtain droplets, and we could account for these droplets. And by sorting the diameter and scaling in order to be mass conservative in the correct way with what we had here, then we obtain the droplets, and we could then plot our PDF here. So it is really a 5-step process. So the shear-walls threshold the erosion to separate the connected liquid, to dilate it so that we obtain such kind of droplets. And then we count these droplets and we obtain the droplet size distribution. And with this, in this G2 configuration, we obtain these results at these different slices, provided the droplet size, droplet size distribution, and we could also obtain the droplet velocity. And this, the first time we did it, it was a discussion to see if it is correct or not. But we see sometimes the physics is reproduced. We have first here very large droplets, and then the number of droplets augment, and we have these two final pictures cannot be correct like this one. So the droplet velocity also is growing with the distance from the nozzle. Having this, we said we need to validate this to see if we can obtain a similar droplet distribution if we base everything on DNS. And that is why we did this DNS. And we use that now DNS BOF method. And for that, we have the same introduction, but I will not like to repeat the same here. The objective was here to integrate the internal nozzle and the atomization in a numerical framework by using now DNS BOF. If we have this BOF, if we have this DNS, this means also that we have comprehensive DNS data. And from that, we can generate also everything we want, the statistic of droplets, and investigate the effect of unsteady injection flow on the structure of the liquid injection jet. We can also be able to analyze the breakup and the spray characteristic close to the nozzle because it is DNS, so it is very costly to go very far from the nozzle exit. It is the spray G, as I told you. So we have 8-hole gasoline direct injection. So this 8-hole, but we will consider only one part here with 1 hole. And this is the series what we have shown. This is this G2, in which we have some flash boiling effect. But in this work, we will focus on G3, where we don't have this phase change effect. So by concentrating on this, we use also the case where we don't have the needle movement to simplify the calculations. And that is why we use now this DNS equation. The continuity equation, the momentum, and also we account also for this equation, but it was not valid because in this WAF we account for the phase change, and here we use the non-filtered part of this equation. I forgot to put the correct equation there. So as I told you, we have this compression term artificially for the based on the relative velocity between the liquid and the gas. And here the compression part, the artificial compression based on the relative velocity between the liquid and vapor. And not only we have this term, which account for the phase change, and we did also, we tracked also the volume fraction of the vapor, not as we did there in LES where it was normalized, but here really the volume fraction of vapor with this artificial compression term, and we have here the phase change, and this is equivalent to this one to account for the density variation. The constraint condition is naturally that alpha for the liquid, for vapor, and for gas must give 1. So we have to deal with primary breakup, secondary breakup. Then this number here are necessary, are required. We have the Reynolds number from the nozzle based on the nozzle characteristic lengths. We have the Weber number and we have Ohnesorg number. And based on this, we will see which kind of primary breakup we will get and secondary breakup. We use this part, so as in the LES, and it is a only 45-degree part, and the inflow conditions is, and the outflow are provided by fixed pressure. We have no slip wall, and we say that we have fully open needle position. The cyclic boundary condition has been also used here, and the mesh is now very, very fine. And we include this condition for the gas phase to fulfill the condition for DNS. And the particle size was resolved at this in this order of magnitude, and here we have 100 million cells. Yeah, we have also in this framework some additional models, and here we have, for example, the Schneer-Sauer model for cavitation. It is the idea how the refinement has been done close to the wall. It is very high, and here it is coarse, and this size vary from 0.5 to 50. So for that, we modify naturally our solver by putting these evaporation models, and also by accounting for the fact that we use here now DNS and not LES, where everything is patent. The first comparison with the experiment was to compare the mass flow rate. The experimental data provided from SCN group and our simulation, so they agree very well. And also the spread angle agree also very well with our the experimental data from SCN. With this good agreement with the reference experimental data, so we can say that we can now track everything correctly and also interpret in a correct way. The first part was to see how the velocity field evolved within, and we see here that we have augmentation of the velocity field at this area, because here we have kind of recirculation here, and the velocity is very low, and it grows and then expand to become in interaction with the droplets which are produced. Then, as we know, there is interaction between the two phase, and the droplets reduce the velocity also of them. So this is the fuel distribution. So we see also that here it is very dense, and there we have the first formation of droplets. And at this area, we see also this line, but there are some droplets which are produced from this part here, because here there is a small film building, and this film disintegrate at this area, and this cause also this jet here. But in all the space, we have this kind of distribution of the fuel. And if we take a look at this different position, we will see in the next slide. So we could now record the droplets distribution which are detached from the liquid core, so that we can plot this distribution at the different positions here. We call them different planes. But to see how this integration take place, we try to first recover the turbulence of the flow, and for that we use the Q criteria with this value here in the gas phase, and we colorate everything with by velocity magnitude. And we see the vortices which are formed if we zoom it, and at this area here we see also, and this cause really the disintegration of the liquid, as we have seen here at this position there. And if we look at the velocity at this area here, this is a plane, so we get this kind of in axial position in a radial plane. No, at this axial plane. So we see the distribution of these different vortices, that they are cut in this way here. Now let us look at the droplet dynamic along the various plane, the jet direction. So we plot, we consider different planes at this position P1, P2, up to this position P8. And the distance between these different planes are of the order of magnitude 0.2 millimeter. So we see at this area that the liquid flow, the liquid is the volume fraction is very high, and that is these small droplets are this droplet I have told you here. I have shown you here. These are these small droplets which are detached from their core. And in going this direction downstream, so we see that we have more and more droplets which are detached from the core. And at P2, we have this distribution here. This is the result from this film disintegration there. And we have more droplet form, and they detached very well. And here we have more droplets, and we can see how these droplets evolve now within this domain. But the question is, what can we do with this? So from this, we try to check some properties and to look at the regime we have from here up to here. Which kind of breakup, which kind of detachment of droplets occur from this plane to this plane. That is what we see here. We have tried to monitor, to do a monitoring of the droplets which occur and to put them in this diagram. The Weber number and the Ohnesorg number, it is the diagram we have seen which allow us to classify the different mode of breakup. In this area, when the Weber number is this order of magnitude, you have oscillation deformation. In this area, we have the bag deformation, the bag breakup, and here we have the multi-mode breakup, and there we have the sheet in it. We see at the beginning that at P1, we don't have really this breakup, but we have oscillation deformations. As we progress at P4, we have now a number growing number of bag breakup. And if we go further, then we will get no bag deformation at P7. So we have only this oscillation breakup. And to see it very well, I plot it again here to see the map of droplets breakup regime for detached droplet structure on the selected plane with at 4 physical time interval of 50 microseconds, and these colors are they are 4 colors and they are for different time. Consider it here. So as I told you, so from P1 we are here, and at P2 we have some more bag breakup. At P3 augment, and P4 to P5 we have also multi-mode here, and after that here we have only this oscillation deformation, which can be considered as the essential mode of breakup at this area. But this was not enough for us. We try also to capture the so-called sphericity. So we have different ligaments, as we know, for bag, from this multi-component, this multi-mode, and from oscillation. We have different filament, but the idea to get to say if really the primary breakup is completed is given by the so-called sphericity parameter. The sphericity parameter, if it is 1, then we can say that the droplets are totally spherical, and below 1, so it is not yet spherical. So that we can say it is the domain of primary breakup, where we have ligaments. And we see this here at P4. We start here at P4 to see the form of the ligament we obtain, and we see here what we have. And here the breakup, the breakup is enhanced so that this part, the word part is the detached droplets, the detached structure from the liquid core, and this detached is not yet spherical, and we see here that it become more and more spherical, but not really equal to 1. So we can say that up to this position plane 8, so we have still a primary breakup. And we try to fit this evolution, it is the function which was obtained for this fitting. It is not linear, but it is quadratic. The other idea was to provide the droplet statistic now. The droplet statistic, as we did, this means that we consider such kind of ligament, and we say that they represent, we can translate them in terms of droplets so that we can have such kind of distribution. So this is the number-based droplet size distribution for these 4 time interval. And this position, this was, this is this position here, P1, and it is P4, and it is P8. And we have this kind of distribution where we did the assumption that the ligament can be translated in terms of spherical droplets, and then we can count them as droplets. This means that we have, this is the outer main diameter, and this is the maximum, this is the maximum of the distribution, and this lie at this point here where we have at almost 0.2 micrometer or such kind of, yeah, I think 2 micrometer. And doing this fitting, we obtain this log normal distribution, and this is what we can provide to LES, for example, for people who like to not to Lagrangian tracking, to say at this position here we have this log normal distribution with this parameter for this quantity here, the variance of logarithm of ln for the SMD, and this is the mean value of this SMD. And we see their development. So their maximum is decreasing with the distance from the nose. We can also do the same for, we can also base this distribution on the surface, but we obtain the same distribution fitting. It is a log normal distribution also, but here based on the area, and we obtain almost the same development. But here we see that the maximum is growing because also of the distance from the nozzle is normally, if we consider the surface, the number of particles is growing. And this is not really here the case where we have the volume. We try to also provide the correlation between the droplet size and the velocity. At the beginning, naturally, we cannot have a correct correlation because we don't have a large number of droplets. And here, this correlation show this profile at this different for interval of time. And we see that the velocity is growing, but the number is growing. And for large particle, we have high velocity. and it become up to p equal to 3, so the velocity remain constant. And this constant to remain the same. Here, almost 100, we can say 200 here, up to this point. And here we see that all droplets, yeah, almost all droplets have the same velocity. We can say this start from from P4. So all droplets have almost the same velocity. This is here we have some deviations, and here, but at these 2 points, we have almost the same velocity for all droplets. And we can say that the liquid loses its moment along the flow direction, and all droplets at this position have similar order of velocity magnitude. Larger liquid have higher speed than the small droplets, especially inside this domain P1 at P1 to P3. And the value of this parameter are here. And this can help also people who are looking for inflow condition for droplet size distribution for such kind of configuration to get this and to use them. And the nice thing was now to validate this, what we did. So these 5 steps to get 2D data from DNS and to compare this with DNS and to see if this procedure was correct. We say that we have first the sampling and we have this threshold. At this point, we did equal to 0.5. Naturally depend on this value, everything, because if this value change, also the distribution will change. So then we separate them by erosion and we delete. We do a deletion and then we count to obtain this distribution of the droplet size. And this is what we obtain for 2D. And if we compare it to the 3D, so we say it is almost the same, but the magnitude are different. And this is normal because this is a 2D and the other one is 3D. And we try to quantify these deviations. This deviation is for the mean is larger close to the nozzle and it converge. This means that this deviation is very small when we are very far from the nozzle. And this is a good news. And we see also the same behavior for the variances. That is very good news which confirm that the process or the procedure we have developed for the LES can be used really, and we can get the correct droplet distribution. And this idea was used for our Eulerian for the WAF Lagrange distribution in their Eulerian part, in their WAF parts where we don't have the tracking of particle. And for that, we can also, in this region, we can really generate also droplets profile, counting for this translation from ligament to a spherical particle. Let now show you how we try to couple this volume of fluid to Lagrangian. So there is these 2 options. There is the option to do buff first and to generate droplets here, as we did before, and to get this distribution as inflow condition for Lagrangian particles. This was as this work from Gauss-Franz. This was also some work done by Hermann, but Hermann was the first to try to make a seamless coupling between WUF, but he didn't use WUF, he used level set and Lagrangian tree. So if we use this, we have seen that the position we will select is arbitrary, and the distribution of droplets depends on the resolution, so that it is very questionable if we do this, but it is possible to do, and people try to do this. But at the moment, I think a seamless coupling is better. We try to develop it and to put it in open form. It is not a compressible solver, but it is incompressible solver. And the first job was to track the jetting cross flow to see if we will get the same result as experimentally reported in the literature. And if we can get naturally the correct Coulomb breakup, we can get also the correct ligament at the correct position, the surface breakup, and so on. All these things depend naturally on the operating conditions. So the idea is that, or the advantage of this is to reduce the computation costs, because if we account for this buff from the in nozzle flow up to dilute spray, I think this will take a lot of time. And that is what we want to reduce, to say that we take only the time to carry out the buff here, the buff, and then to make a seamless transition to Lagrangian, where we can have very coarse grid, and then we reduce the computation costs. And the question is how we can really validate this. The objective of our work was this year, to investigate the characteristic of the complex spray atomization of liquid jet in cross flow. But I have seen that at your institute, you also carry out such kind of simulations, but it was in another configuration. And what I think you carry out at the institute. So the numerical method is very simple. We have the volume of fluid method, and we have also the Lagrangian particle tracking. We have introduced these at the beginning of this lecture, and this is the definition of our liquid volume fraction. We use only two forces in the Lagrangian part, the drag force and Lagrangian, and the gravitational force. We know now why we use only these two, and that is what we have tried to demonstrate, and we demonstrated in the past, in the lecture, I think, of the second, the third lecture, I think. So the UP is the parcel velocity. It is the mass of the particle, and the position here by particle. We understand droplets and the force are what we have here. The Lagrange particles, so we have introduced this also. How we do the coupling? So we have first the WOF solver, and from the WOF solver, we try to clarify everything here. We have the WOF, we track the volume fraction, and here we have this kind of filament of perhaps droplets. And then we try to identify the droplets with a specific diameter and specific sphericity, as we have seen in the previous in the DNS part. So after identification, so we use some criteria. We define a limited diameter, and we say if the diameter is smaller than this value, threshold value, then we account and we consider this particle as droplets. And also it should fulfill these two conditions. And these also say us that if the sphericity is, for example, 0.8, then we can say we have our particles. And we can track this particle in Lagrangian way. This means that we segregate, we separate both from these selected droplets. And after that, we take these particles and we track them, and they are subtracted from these both parts. And it is what we do here. So that is, everything is put together in this scheme. We have the identification of droplets. We calculate the droplet properties, and we do the conversion criteria. And if these criteria are met, then we say we have droplets, we delete them from the WOF, and we eject them as a Lagrangian particle, and then we solve our LPT, Lagrangian particle tracking, to the end. Here we consider this jet in crossflow. I am looking for the name of this, the author of this experience. So Mr. Sun forgot to put them, the name, but they are, I think, in our paper. So the fluid, it's air. The velocity of the fluid is this here, the density, and for air we have this. So the mesh characteristic is provided there. So we have different planes at which we will generate our data, and we have also experimental results at this plane. So the jet comes from here and the air here, and we have this behavior of the spray. To show you only how we did the meshing, so it is adaptive mesh, and it is refined where we have droplets or ligament, and it is at the beginning we have 4.5 million, and the smallest size was so much. And after adaptivity, after adapting the mesh, so we come up to this 8 million, and the smallest cell was cell size was 7 micrometers. The safety code is open form, and it is incompressible, and this allows us to get this kind of result. First, for the penetration length, and we obtain this penetration length in a very well agreement with experimental data, and it is the trajectory of our jet. And in another paper, I think we try to compare them with the different correlations which were derived in the literature. And to zoom this part here, we see that we have really this a column breakup at this part. And we try to highlight the Lagrangian particle and also to show still where we have ligaments. And here to show only what we have once adapting the mesh. So this mesh is here very fine everywhere we have buffs, volume of fluid, and here it's become coarse where we have particles, and to remain here very fine where we have volume of fluid. So to compare the experimental data with numerical simulations, we first show that the velocity involvement here involve within the distance of the nozzle, and this causes the spreading of the particles within the system. And this velocity, so with the increasing air velocity, we have a large spreading of a Lagrangian particle along the axial axis. We try to compare now the outer mean diameter with obtained with our calculations with experimental data, and this can be seen here at two different positions. So at Z to D 30 and Z to D 60, and we see that our results agree very good with this experimental data. We have also the jet velocity has changed, but we didn't provide the results for that. We only use these inflow conditions, what we have here. So so the next question was how to get the PDF. So we got the PDF at these different slides I have shown you, and for jet in crossflow, the best fitting was with this Combustion profile, and it is almost the same at this different position we have there. We could now compare also the velocity along the channel, and we could also compare the SMD. Here, for these two positions which were here recorded, these two positions, so we get really a very good agreement. We can say it is very good. And the velocity is increasing with the distance from the nozzle. That is what we have said. And with this increasing velocity, then the particle spread more within the computation domain. We did for jet in crossflow, and the idea was here we don't have experimental data for combustion. Then we move to a configuration in which we have also experimental data for wheeler. Now it is already available, but it is very new, and we don't we have not yet included this combustion in this framework. This is this configuration from Korea. It is from Rouen in France, CRSB configuration. So we have the fuel jet is entering here, goes there, and the air come here, and here produce a swirl, and we have the swirl there. And it is how to show how this swirl is working. So that this here come there, and we have the swirl here, and we got the swirl spray, and this is these two. This is this here, and there we have these two channel which allow to produce here this swirl around this around the liquid, so that at the outside we have a swirl spray, which is really interesting to investigate by means of this seamless or real-time copper dwarf and LPT. So we have seen different kind of nozzle, and this is a pressure swirl atomizer, and it's allowed to produce a very large spreading of particles. So the cone angle is high. And this, the idea is to investigate first the complete spray atomization, and then to account for the combustion. So we generate then to account for this augmentation of this, the spreading of the jet. We generate this kind of computation domain. So we have the orifice here, the sphere chamber, and we have our tangential inlet flow ports, which allow to generate the flow, the swirl at this area. Here are the dimensions, and I think this configuration is open for each group. I think also your institute will participate in investigating this this configuration. So the fuel is an octane. The inlet condition, density, viscosity, pressure are all provided, and we use our CFD solver in the open form. The meshing is also here really we use also the adaptive mesh generation. The initially we have this number of cell, and the smallest is so, and at the end we have 25 million, and we end up with this smallest cell size. The position at which we have experimental data is this position. I think it is 6 millimeter from the nozzle, if I have it correctly in mind, and I think it is so. If I see what soon put in these slides. And there we can see the droplets which are generated, and there we see also that it is very good refined in this area, and here not really. So the results we obtain are here. First, the spray cone angle. It is almost from experiment. They provide us this angle of 92. And from our calculations, we have obtained 95. So there is not a big difference. So 3 degrees for such kind of configuration. We don't say that the experimental result is the correct one, but we are in the, I can say it is very good. It is a good agreement between both. So the quantitative error is around 3%, and we underpredict. It is, we overpredict this in this way. So to follow now the spray evolution, we separate these domains. So we have the secondary breakup and the primary breakup. And this is the area where we have dense spray. And here we have dilute spray. And he is now trying to characterize everything in a detailed way. This means we will get the Weber number here. We will get here the breakup regime. And he's doing this now. And this is what we would like to report in the next symposium in Egypt and during our TCS, so the turbulent combustion spray workshop. And here it is a view of the results. We see that we have the liquid sheet breakup at this area. And then we can also see here the ligaments which are produced at this area here. And we can also select here the droplets we would like to track as Lagrangian particles. And at this area, we have really dispersed spray where we see that the volume fraction or the density, yeah, we can say the volume fraction is no more very high compared to what we have. So this is what I meant. So the first profiles we have are from this plane at 6 millimeter from the nozzle. And if we have a view on this surface, we see that the particles are collected around this in the annular region, almost no Lagrangian droplets in the center of the droplet because of this swirl motion, which try to bring the droplets in this annular region, and the velocity reaches highest value at the central part of the annular region. So we will see, I think, didn't show it, but we see we have here the diameter and we have the velocity. So the velocity is very high at this region and not here, where we have very, very, it is empty from particles. From the results, from experimental results, so we deduce the droplets size distribution, and the result we also obtained from simulation was produced here, and we tried to make a fitting. So the fitting is also a normal fitting, as we have seen in the IC engine for the spray G. And this is the number based, and here we have the mass base. So naturally, here we have a big deviation. It is perhaps due to the mass conservation, which is perhaps a problem here where we track the particle and we didn't include here the two-way coupling to make everything mass conservative, really mass conservative. So that is the result I would like to show you. I think we can conclude now. So the first part was to show the DNS for the case with for the SCN spray G case. I show first the G2, where we use LES, in which we propose a way to generate the droplets also using LES. And then we apply DNS evolved to this case, and we try to show how we can generate the 2D result from the 3D and how these correspond to what we have produced before. And it is what we would like. We are doing this now to carry out also G3 using LES and to compare this result with the result we obtained here from this DNS. So the DNS allowed us to generate comprehensive database and which can be used for LES model development and validation, as I told you, and these include, among other, primary breakup we have characterized here. We have also include cavitation, but I didn't show the result with cavitation inside the nozzle. We use the model by Schneier and Scheer and Sauer, and we have also generate the secondary breakup a map, and for the primary breakup we have introduced this kind of sphericity and the spray. Then we are in this domain with this sphericity between the primary breakup and secondary breakup. That the end of the secondary breakup should provide a sphericity equal to 1, but we didn't obtain it at the moment because we are very close to the nozzle and we could produce a comprehensive data to characterize the spray, including droplet statistic and also suitable fitting functions. So this DNS was carried out without accounting for the needle movement. And we will like also to include the impact of cycle-to-cycle variation. This means that we will try to mimic the in-cylinder flow at the outlet and not to provide this condition what we had at the outlet. And using this, we will try to see how this condition influence the spreading of the jet from the nozzle. So with this will be done by LES, and this also will be done by LES, where we will include all the 8 holes in their simulation. At the moment, this part is running for DNS, only for the 1/8 part of this configuration. So we have also here tried to show you how at our institute we are coupling in a seamless way WOF and LPT, and we have compared them with the experimental data from the literature. We didn't carry out the experiment for that. And the characteristic of the complete spray atomization will be well captured. We did it for 2 types of configuration, the jetting crossflow. I think we can also use the jetting crossflow in the future, but here we got it from the literature where we had 2 operating conditions. And we have also applied this to the configuration from OR. And these results from OR, we will try to present them at the symposium in Egypt, I think in January. The results show the good capability of the present method to resolve the complete atomization process from pressure sphere atomizer. And the next step is now to couple it to combustion modeling. And at this point, we will include the stochastic field, Eulerian stochastic field, to account for the turbulence chemistry interaction, and then we will use naturally tabulated chemistry for that. It is NF10. We have already tabulated chemistry for that. We have only to update the operating conditions. And this is our next step in the next month. So I think I can close my lecture here, the presentation part. And I think it is better that we get discussion for the last 30 minutes. That is why I give you the word, and so that we can be ready to get some questions. Thank you.
Yeah, thank you, Professor Sadiki. It's wonderful to have this lecture series. Yeah, I mean, participants, if you have any questions, any doubt, anything that you would like to have discussion, I mean, you can raise your hand. I'll allow you to talk. Anybody has any question, anything that you would like to talk? I think they are quite.
Love that the 2 first days, people try to put questions. And after that, I don't know if the matter is is not what they. And the two first day, I think it was very, very rudimentary.
There is a question. Yeah, I can allow Kamal to. I can allow you to talk. You can unmute.
So here the question is it possible to get PDF lectures?
Yeah, sure. This one actually I can answer. I think some of them have been asking, but I have to check with two different things, especially the IP issues, intellectual property issues. So I have to check with this course coordinating institute and also our institute. Then only I can do anything. Videos are already I am sharing with them. But the lecture notes, I have to first check.
Okay.
So that is what I have been initially responding, probably not possible because I have to get a clearance from both IIT KGP and our institute. That's why I've been, so that I will clarify probably by next month. Anyone has any other questions? I mean, you can. Yeah, another. I mean, some. Okay, I'll go back to things.
Yeah.
You just said that this, yeah, this Korea Warner we are also simulating.
Yes.
And I think next week, okay, let us see. Okay, I will allow him to talk. What's his name? Yeah, you can pose your question, unmute and Bala. Bala, you can unmute and talk. Yeah, his question is metal particle combustion, but what, I mean, then what? Metal particle combustion do what? I mean, question looks incomplete.
I didn't get the question.
Yeah, exactly. I also didn't get the question. Maybe you can be a little specific. What do you want to get clarified? Yeah, since it does that, meanwhile, so this this particular geometry, this yeah, our actually is the compressible framework, but I think the algorithm is pretty similar. I mean, same probably. Mm.
Yes.
But only we are lagging behind because we started in, I think, month of November only. So once I said that I would like to participate, then they said the CAT file and things like that. So we are lagging behind. I think coming week for next 14th, I think there is a meeting again.
Okay.
Now you said you are planning to couple with the combustion.
Yes.
Here you want to do with the already and stochastic field, right?
Yes.
I'll go back to my question in the earlier session this morning. So,
Okay.
mm, so Eulerian stochastic field, you will, so this will be active both in Eulerian phase and Lagrangian phase, right? Or
Both.
Eulerian phase only you will consider the evaporation, then when the particle gets converted, then only you will consider the combustion. What is that?
Yes.
I mean, how would you like to, approach that?
The question is how I would like to.
Yeah, I mean, see, the Eulerian phase, there could be evaporation, right? The ligaments and all these things, they can evaporate.
Yes.
And their combustion may also take place. And
Yes.
another portion would be when the particle converts to dilute, particle, then again, that can be, ready for combustion. So there are two portions where combustion can take place. Now, how are you thinking about that? I mean, see, once the ligament breaks and you get the particles, then that portion is clear that there would be combustion taking place and the ESA would work.
Yes.
But in the ligament, that may also evaporate if you have a high temperature.
Yes.
And then, so how is Eulerian field is going to be kind of coupled in that part?
This part. So we will introduce the system of evaporation. Will be there also.
Okay.
In the Eulerian part. So you have the term which for the system coming from the
Hello.
liquid.
Yeah, Anurag, just hold on. Let him answer this, then you can continue.
Okay, sure.
Okay. So we have one term, additional term in the field. Okay. Eulerian stochastic field. And this term I showed you yesterday that these account for the effect of the liquid phase to the gaseous phase. So we have two source terms. We have one source term from chemical reaction.
Yes.
We have another source term which comes from the liquid.
Okay.
Is source term consider this effect, what you are speaking about?
Okay. So if I understood correctly, that means still my WAP and LPT would work. And then only for taking care of the combustion, ESA would work, right?
Now you have first to extend your stochastic field, Eulerian stochastic field, to two-phase flow.
Yeah.
So to include this source term, this additional source term. If you have it, then it is okay.
Yeah, Anurag, you may ask.
I hope I answer the question.
Yeah.
Sir, hello, sir. So my question is, it is not regarding the simulation. So sorry for that. So my question is, for a TFI injector, is there any range of droplet sizing for better emission? Means we know the smaller the droplet, the better the emission. So is there also a minimum cutoff that we cannot go below that or something like that? Is there any range?
I didn't catch the question exactly.
So
you have.
Yeah. So what do you mean by PFI injector?
Port fuel injector working below 5 bar.
Okay. So his question is if, yeah, I mean, for PFI injector, which operates below 5 bar pressure. Now, is there any recommended particle size? I mean, atomized particle size, which can reduce the emission? That is, I think, his question. Am I right?
Yes, sir.
Yeah, I think this question is related to the design of the nozzle, yeah, for the atomizer.
Yes.
Yeah. And I have no restricted range, but I think you have to carry out some sensitivity studies, okay, which can help you to get the correct droplet size, which should be generated to get less emission.
So it means it's a kind of hit and trial method. Means we can go for the different sizing and see what is the effect.
Yeah, that is what I can suggest at the first.
Okay, okay, thank you.
Yeah, but there is some correlations. I provide them, I think, in one lecture. So the correlation which relates this the outer main diameter with the dimension of the nozzle.
Yes.
Okay, and I think I don't know if you were there and you have seen these correlations.
Yes, yes, I have seen that. But
Yes. And from
yes,
this correlation, you can estimate the dimension of the nozzle depending on what you will get as at the outer main diameter.
okay,
Okay.
okay, okay. Thank you, sir.
Okay.
Actually, if I little bit add on to that, see, most of the commercial injector, they have a specified range that what it can atomize
Yes.
to,
That
and
is
that kind of an design data. Okay, and when it was designed, those kind of data base was prepared, obviously both based on your simulation and your PDPA measurements.
Yeah.
I mean, any nozzle design or injector design, they go through that kind of process. I mean, obviously these days your CFD complement that thing should reduce the downtime, and finally you do PDPA measurements and then characterize the injector. So those are mostly come from original manufacturer, and they provide the range of what it can atomize to and what would be the size of the particle that you would get after atomization. Okay. So that's more done at the design level.
Yes. And but if you want to design something himself, then he has to take this correlation and to get the correct nozzle. If he has the possibility to design it, then he can design in this way.
Okay. So one more thing. So is there any possibility to design a swirl injector for PFI is below 5 bar? It's just a question just hit my mind. If we can design something for below 5 bar, something swirl kind of injector. So will it help in reducing the SMDs?
So you are now, I gave also the correlation which relay. There we have the penetration length as function of the pressure.
Yes.
Yeah, you have this, and they provide you this correlation, and you can also, based on this one, you can relate it to the diameter, because there is a factor there which is also function of the nozzle. So I think it is a Hashimoto correlation, but it is in one slide. You can also get it.
Okay. Okay.
Yeah. So, Bala, can can you frame your question?
Sorry, sir.
No, no, not Anurag. Bala is metal combustion, metal particle combustion. So it was an incomplete question. So, yeah, let us see what about others. Any question, any query that you might have. Now, this inside nozzle, there could be these things, right? I mean, cavitations.
Yeah.
So,
In this
how,
from ROA.
not ROA, I mean, in general, if
Okay.
you,
Yeah.
the cavitation is a big issue, right? Inside the nozzle.
Yeah.
So, what is your comment and that how, I mean, BOF would be capable of handling that cavitation, or we need to do some more modification to the equation system and things like that.
Not really a big modification, but you have only to introduce a cavitation model.
Cavitation model, right?
Yes, like in the work I have shown you.
Mhm.
So there is also a cavitation model, but I didn't show you the results. And
Okay.
you using a cavitation model, so you can capture this in a correct way.
So that means VOP with the cavitation model should be able to do that, right?
Yes.
Now, okay, so I'm extending the thing a little bit further. So when you have this superheated fluid or
Yeah.
fuel, then their flash boiling occurs.
Yeah.
So how do we handle that? Because that's the atom. So that allows to have some primary atomization close to the nozzle injector exit.
Yeah. Yeah. So there is also in the spray G2, it is a we have a flash boiling effect. And there is also a model which account for this effect.
Yeah,
So
that's a correlation is there. So
yeah, in this model. And that is the model we have used exactly in this case.
okay.
I can send you one paper for where we presented it. So
Okay.
we have this cavitation and we have also this flash boiling effect there.
Mm.
It is possible to do it.
Yeah, that Stuttgart group, they had a lot of data. Actually, we did
Yes.
some
Yeah,
analytical
yeah, yeah.
modeling of them.
Yeah, it was in the framework of a project in which also I was involved. The project Transregio 75.
Mhm.
They carry out DNS data for flash boiling a spray,
Mhm.
and they generate a lot of um, data, but they didn't develop model.
Yes, they didn't develop any model. Actually,
Yeah,
we did some analytical work and when I was there actually.
yeah.
So then we tried to propose some model,
Okay.
some correlations. Mm. But close to exit is fine, but when you go little downstream there.
Mhm. So then I will send you also the model we have used,
Okay.
so you can compare.
Yeah. Any other questions or any other things? Any comments or anything? So let's, put some philosophical question or discussion point.
Yes,
So
okay.
this clean zero emission, or every country in the world now saying that net zero, net zero. So how are you going to replace our conventional combustion in next 30 years? Is it really possible? I think Germany took some decision by 2020, 30, they would do something.
Yeah, these are expectations.
Wish list.
But from my point of view, I think it is difficult. We need combustion, and we will need combustion also in the future. But the problem is perhaps the question is to make a balance. So people try to consider the process before the generation of the fuel and the process when the combustion takes place. But if they make everything together, then they will see that it is not zero emission. And from combustion, it is very difficult to get zero emission. Even if we are speaking about a metal fuel, so it is not zero emission. So the emission is perhaps less, but not zero. And if we try also to use some biofuels, to use also some fancy fuels, it is not zero emission. And the best way perhaps to get zero emission is to not consider combustion. And then we have hybrid is also with some emission, or to consider only electric devices, electric-based engine. Then, okay.
No, I mean, then I have a different take on that. Actually, if you say electrical, that way you avoid combustion, maybe you have so-called zero emission. But now the pre-processing part and post-processing, like
Yes.
the
Yeah.
battery, recycling of the battery is going to create a lot of hazards.
Yes. Yes.
We are not touching upon at all.
Yeah.
And now manufacturing of the battery also.
Yeah.
So you are using a lot of electrolytes and things like that. So we are not talking about that.
Sure. That is what I have said. If we separate both, then yes. But if we put them together, very difficult.
Yes.
To speak about zero emission. So
I mean, like two big industry like automobile and aviation industry, they have to shut down, then only combustion can be stopped, immediately. Or their fuel replacement is not there. As simple as that.
Yeah.
When any bioethanol, the production is not there. Whatever demand, the supply is not that much.
And the question is also to see which is priority in European countries and in other countries which are trying to develop. I think that the priority in a developing country like Germany is different from priority from India or China. And it is not very fair to think about zero emission in India. I think it is better to speak about less emission and not zero emission. And here they can also speak about this, but I think they cannot reach this target. It is difficult. But it is a good thing. It can promote research and it can also boost the industry. But the other countries who need, which need at the moment also a very great development boom, I think they need still a combustion for different purposes, for production of energy and also for electricity and for energy. And in automobile, in aircraft, everywhere they need combustion. And I think perhaps the post-process to combustion, this is perhaps the thing on which we have to discuss as we did for the exhaust after treatment. So the combustion is there, but we try to reduce its negative effect. And that is perhaps also which we can do for different kind of system in which combustion is used and in which electricity is produced.
Yes. That's very fair to say. The requirement or priorities in developed country and developing countries are totally different. And
Yes.
especially even if you're talking about these processes, but more about the metal industry, especially electrical steel industry. They
Yeah.
require huge furnace. That without combustion, how would you provide that?
It is difficult.
It's just next, and without metal, then no development would happen.
Yeah, that is so.
Hmm.
We've submitted a project, it is a European project,
Mhm.
in which, though the title is the volatilization based on, I think, based on synthetic fuels for industry intensive, for energy intensive industries.
Mhm.
The example is these steel industries, cement industries. They cannot work without a lot of energy, a lot of electricity. And this is what really is challenging also here. And for that, the idea is only to say we can use some fuels which help us to reduce the emissions, and and if we reduce the emission, then we can control this emission, and perhaps there is a post-processing way to make it zero.
Yes.
So this is also questionable.
Yeah. So question is that along with, you can see, or shall I read it out?
Yeah, please.
Yeah, along with hydrocarbon fuel, if
Yeah.
we boron metal particle in atomizer, which model of analysis will use for droplet study?
Which model?
Yeah. So is the question is that you have hydrocarbon, then with that you inject boron particle inside the atomizer.
Mm-hmm.
Then what would be our method of analysis from modeling point of view?
So if I understand well, we have a three-phase flow.
Yes.
Yeah. That if we Lagrangian is okay, I think.
I think Eulerian and Lagrangian would work. You have to have a marker for the second solid particle. It's just like an coal combustion, things happen in that way. But anyway, coal gets, pyrolysis takes place.
Yeah, it's something like that, but
Yeah.
perhaps there will be a problem when we generate the table, if we would like to make it tabulated.
Yeah.
Because at this point, we will have different mixture fractions,
Mhm.
and we will have a yield table
Mhm.
in which we say, for example, for coal, we did it with two mixture fraction. There is also a group in Japan. They try to do the same. We reduce then these two mixture fraction, and we put them together to get a suitable table. But at the end, we are able to discriminate these two mixture fractions. But I think with such kind of aspect you are now speaking about, I think then it will be difficult to reduce these two mixture fraction to one, but there we have to take 3 or 4 mixture fractions to deal with such kind of systems. if we want to tabulate it, I think the problem there will be to tabulate. Otherwise, it is possible to solve it if we have the correct chemistry. And naturally, the first step can be to make, I don't know, as we did also with coal, we can start with very simple one step, perhaps one step is not possible, perhaps 6-step mechanism. We can reduce this and try to calculate for these three phase, and each one for, then we will have a huge set of equations. But I think tabulated chemistry will be well appropriate.
Yeah, I mean, it's actually another way to, I mean, if I think a little bit, I mean, another way to, we may have separate tables for boron and particle oxidation and second phase hydrocarbon. I mean, two different kind of tabulations we can do, not a single tabulation. But yes, I mean, somewhere then inside the main program, we have to kind of make the connectivity, because you will get temperature from both places. So it has to some sort of a mixture, weighted something we have to do.
Yeah, one can do also in this way, but I think it will be huge.
Yes, it would be huge.
Yes. If you combine both, I think it is easier as to follow.
That's true. That's true.
I think to follow the path that we use for coal combustion, I think it is better.
Okay. Yeah. Any further questions or any other query anybody has? Good. Looks like they don't have any other question. Yeah, it was really fantastic last 5 days. So I hope they would learn something out of it and may adopt few things in their future research and things like that.
So I think so too. And I would like to thank you first for the invitation and for the whole staff of your department, to give us this opportunity to share what we had here and to discuss about these open questions. And I would like also to thank the financial support of these activities and also all participants, for the attention they reserve to this. And I think they will get also the time perhaps to discuss after that, to point some other questions and perhaps to make some contact, supplement some fruitful contact. And I hope with this, colleague Ashok, that we are in the best way to continue this collaboration. And I hope we have we have a lot of things to do together.
Yes.
And see that our interest is really very, very huge. So the field of our interest is very, very huge, so that the collaboration will be continual, and it is my hope that we will do this. So again, for everything and for coordinating everything, and for giving me this time to discuss with all colleagues from India and or from outside, perhaps. So there are some participants from outside, I don't know. Okay, thank you.
Yeah, thank you for your nice concluding remark. Yeah, there are some from outside. They were present on the first and second day. Then slowly I saw them. Probably the time difference and things like that. Yes, we'll continue our discussion and all these things. And I hope participants also probably enjoyed the things. And if they have some specific concern, they can always write back to us. Yes, and I would also like to thank the funding agency, which is under this particular banner. They are supporting this kind of activities. And obviously, thank you for accepting. And I mean, it was COVID time when we were supposed to do this course. So, but this, finally, we had it.
Okay, thank you.
Yeah, thank you. Thank you.
Okay.